introduction to the lambda pi calculus we will be writing. And at the end, I hope I will have some time, some practical session. I hope at least most of you installed lambda pi on their machine. So you remember perhaps yesterday we finished on this slide with all the rules for LF, so for the lambda pi calculus. And so this is a presentation that is to Harper and Salomon Blanqui, beginning of the 90s. And so you remember there are typing rules for typing environments, for objects, for families. And families are the arities of objects, and for kinds, which are the arities of families. Okay, so you have this hierarchy. At the bottom, you have objects, and then families, and then kinds. But you can also see that there is many similar rules. Okay, so actually we can factorize these rules, and this gives another presentation, which is called the PTS representation of penetration, which is due to Berardi and Terlo at the end of the 80s. And the idea is that we introduce a set S for sorts. So remember the two constants that we have added to type families and type kinds. And then, so all the rules we had before, we only have these ones now. And so you have the rules for typing environments. And then we have one rule for each construction. So you have one rule for abstraction, one rule for application, and one rule for the product. And here, one rule for typing the big type constant. And then also you have the conversion rule on types, which includes so families and kinds. So like this, we get a presentation that is much more compact, but we are losing this intuition we had before of this classification we had between objects, families, and kinds, because everything is blurred in this presentation. Okay. So the previous presentation is nice because we better understand what is going on. Okay. But this one, of course, is better for doing proofs because you have less rules. But we can go further, and this is what actually they did at the end of the 80s. So why adding only two constants? Why not taking any set of sorts? Okay. And keep all the same rules, but now to parameterize all those rules by a set of sorts S by a relation between those sorts to say what is the type of a sort, okay, and also another relation on pairs of sorts and sort to describe what are the possible products that we can do in this system. So it's a generalization. So we parameterize all the typing rules by this set S, this relation A, and this relation P for products. Okay. And so what's the interest of all this? So I summarize again here. So the PTS, what is the PTS? So we have a set of sorts, the relation of sorts, typing the sorts, and it's the relation for products. Okay, and we say that such a PTS is functional if the relations A and P that we are considering are functions. Okay. In this case, so we can prove actually. So for this kind of system, we can prove many properties. And so one that is interesting is that if A and P are functions, then we have what we say uniqueness of type. Okay, so actually it's not unique, but it's unique up to beta equivalence, because we have this equivalence on types with type conversion. So it's a nice property. And so what is the interest of this is that actually we can find, using this presentation and different relations, find a well-known type system. So the first one is just simply type lambda calculus, okay, where we can form eurotypes between types only. This is the only thing we can do, and it corresponds to the previous pool. If I have to type, I get a type. But then we can also have type constructors, like in programming languages. If you take a list of elements of some type, so polymorphic lists, it means you need a constant taking a type and returning a type. And for typing this type here, you need a new rule. So a product on kinds. Okay. And you can also encode here as a PTS dependent types. So the system LF, the lambda pi calculus itself, okay, where you have some constants having this kind of arity, so a type, a row, a big type. Okay. And to type this type, okay, you need this product rule. So a type, a kind, gives a kind. And finally, if we add the product rule kind type, okay, we then we are able to type the polymorphic identity, any polymorphic function, actually. And you see that to build this type and to check that it's a correct type, we need this rule here, because big type is a type kind, and here we have types.
The simply type calculus, the rows are only using types, so do you really need the kind solution?
That's a good question. I mean, we need the kind just to type a big type, okay? But actually, it's not really.
So if you remove kind from the source and from the action, you still.
Yeah,
I don't recall the rows.
So. Yeah, so the problem is that your constant big type is not typeable, but perhaps it's not that a big problem. So yeah, that's a good question. I do not remember the answer. But actually, so yes, it looks like you get more things, but it's, well, perhaps it's very similar. Okay, and yeah, so small remarks. So you see that in all these rules, so we have all the cases, but each time, you know, the output type is the second argument. Okay, so here we have type, get type. Here we have kind, we get kind, and so on. Okay, so we have this property, but actually, so the product relation is very special. The second relation. And so we can put all these things together, and we get the famous lambda cube. Okay. But what is interesting to remark, so each one of these product rule we have, okay, corresponds to a specific feature. Okay, so we have seen, so for simple types, then if we add polymorphism, we need to add this rule. If we want to have dependent types, we add this rule. And if we want to have type constructors, we have this rule. It's completely modular, okay? And you can get like this 8 different combinations, okay? And it forms a cube depending on in which order you add the rules. Okay, so either adding so type constructors, polymorphic types, or dependent types. Okay. And so this is the so we get this hierarchy of type systems that are very important applications in programming languages and systems with only two sorts. Okay. But in general, so in PTSs, you may have much more sorts, and in some proof assistants, indeed, you have many more. So, for instance, I simplify here a little bit. In systems like Agda, Lean, Rock, they use actually an infinite set of sorts. Okay? And in Agda, it's called set with some index that is a natural number. And you see that the axiom rule says that set I is of type set I plus 1. So you can see the constants we had before, type and kind, they correspond in this case to set 0 and set 1. And for typing products, okay, in order to keep something that is predicative and not inconsistent, we need to make sure that when we are building, we are making a product of a type in set I with a type in set J, then we get something in the max of it. Okay, and so actually there is something a little bit more than this, you know, but I will not enter the details. In Lean, it's very similar. So instead of set, it's called sort. Okay? But you also have this hierarchy. And one important difference is that so sort 0 is actually called and written in the code prop. Okay? They are equivalent. And this is the sort that is used to represent propositions. Okay? And it is at the bottom of this infinite hierarchy. And an important difference is that you can build a proposition by quantifying over any type of any sort. Okay, and so this is what we call some impredicative system. And this is fine to do this for propositions because this is the smallest universe in the hierarchy. But you cannot have two impredicative universes at any stage. Only at the bottom. And finally, so all these systems are functional. Okay, so we have functions for these relations A and P. Okay. And in Rock, but it's also there are some systems like Rock where it's not functional anymore. They introduce some subtyping. It's called cumulativity. Okay. They introduce some subtyping on sorts. Okay. So it means it's not functional anymore because type can have different types. Okay. But we can prove that term can have a smallest type in this order. And so what is the interest of this subtyping relation here? It means that any object of in some universe I is also an object in the next universe. Okay. If you don't have this, and this is implicit, okay, if you don't have this, then you need to define some explicit function to move an element from one universe to the other. So they are kind of equivalent, but here it's implicit, and here you need to be more explicit.
Is there any reason why you don't allow subtyping on the first argument? I guess you have to switch the order, of course.
Yeah, well, so there's various reasons. So I mean, the meta theory is much more complicated, yeah. And I don't know the details of this, but I think it may create some problems with some other features. Okay, so
I've read discussions about this between the code developers, and they don't all agree whether it's consistent.
yeah, I think exactly. So
Something is consistent, something is inconsistent, but we haven't written it.
okay, but let's go back just to lambda pi calculus. Okay, so just simple types, dependent types. So you remember we have seen yesterday, so the properties of simply typed lambda calculus. Actually, all the properties we have seen, they are preserved when we add dependent types. Okay. So types are not unique, but equivalent modulo beta equivalent. Okay. Beta reduction terminates on all well-typed terms. And type is preserved by reduction. Okay. And also the problems of type inference and type checking are decided. So that's why, I mean, the lambda pi calculus is a nice system because we have all these properties, and we are going to see that how dependent types can be used to encode over systems and still be decided. So now I'm going to introduce the notion of signature. Okay. So until now, I just spoke about having a typing environment for local variables. Okay. But we can make a distinction between variables, you know, because often we are working on some given theory. Okay. So a part of the typing environment that are the global constants we are going to work all the time with. And that is kind of fixed at the beginning. But because to handle abstractions, we have also local variables. So now I'm going to split in two. So the fixed part, this is what I'm going to call the signature, okay? That is providing so the global constants. And then you still have local variables in gamma. Okay. So sometimes I just I may not write sigma anymore because it's kind of implicit. This is the ambient theory in which we are working. Okay, and so we have seen that we can modulo beta equivalence identify two types, like this one, for instance, array with the identity function applied to 3 and array applied. And we have seen the example of concatenation on arrays. Okay, that if we concatenate an array of size 2 with an array of size 3, then we get an array of size 2 plus 3. Okay, so that's nice, but in practice, we want to identify this type here with this one, array of size 5. Okay, but at the moment, it's not possible. We have nothing saying that these two types are equivalent. Okay. And so this is where, I mean, it may be useful to introduce more reduction, okay, than just beta reduction. And so this is the goal of adding rewriting, is to be able to identify more types using rewriting. So I'm going to give you some very brief introduction to rewriting if you are not familiar with this. So it's a theory that has been introduced in the 60s by Knut, especially, in order to solve problems in equational theory. Okay. And so a rewrite rule is nothing but an equation that you use only from left to right. Okay, so it's an oriented equation. And the idea of rewriting is to apply these rules as long as you can in order to simplify some expression until you reach, hopefully, a normal form. And so it means, so when you have a subterm that is matching the left-hand side of a rule, you replace it with the corresponding right-hand side. Okay. And so this framework, just rewriting without talking about typing, it's like lambda calculus, it's a Turing complete paradigm. So it means you can, using rewriting, you can encode any recursive function. And so why it has been introduced, is to solve problems in with some equational theories. Okay, so assume you have a set E of equations, okay? And I denote by this relation here the equational theory that is generated by those equations. Okay. So this is the closure by reflexivity, symmetry, transitivity, context, and substitution of the equations. Okay. And so one interesting problem, is how to know that when I take two terms, whether they are equivalent in some given equational theory. And one way to solve this problem is to try to find a rewrite system, okay, that is terminating and confluent, okay, and that has the same theory as the equations. Okay. So in this case, we can decide the problem. Why? Okay, because it terminates, it means that any term has a normal form. Okay, so we can compute the normal form. And so when we want to check the equivalence between two terms, okay, so we compute some normal form, T prime, U prime, okay, and because the system is confluent, okay, we know that normal forms are unique, and so we can just check the syntactic equality between the two. Okay. If they are equal, then they are equivalent in the theory. Okay. Okay, and so now, using this tool, okay, we are just going to extend the lambda pi calculus by adding some rewrite rules by using rewrite rules in the type conversion. Okay. So now, in this framework, so lambda pi calculus modulo rewriting, so we assume given a signature for the global constants and a set of rewrite rules, okay, on these global constants. And then we have this typing rule, okay, that identifies types modulo beta reduction, but also the user-defined rewrite rule. So a small remark, by the way. So I remember it was mentioned yesterday by Andrzej. So this rule is not symmetric. Because here we are checking that A prime is typable, but we do not check that A is typable. Okay? But this is something that can be derived. Okay? It has been mentioned by Andrzej. So when term T has some type A, it's possible to prove, it's not very difficult to prove, that either A, so in the context of the lambda pi calculus, either A is a kind, so kind is a constant for typing kinds, but kind itself has no type. Okay? So either A is kind or it is typeable by some sort, can be type or kind. So actually, we could have a symmetric version of this rule. Okay, so to summarize a little bit, so now what we are going to consider is theories in this framework. Okay, a theory, so it's given by a signature, so a set of constants with some types, and a set of rewrite rules defining those constants. Okay. And in addition, so we assume in order to preserve all the good properties of the lambda pi calculus when we are rewriting, we need to make sure that a number of conditions. Okay. So to preserve decidability, we assume that the combination of beta reduction and rewriting terminates. Okay. And in order to preserve important properties, we also assume that beta reduction and rewriting together is confluent. Okay. So it means that any term has a unique normal form. And also we need to make sure that rewriting, indeed, like beta reduction, preserves typing. Okay. We don't want to rewrite, for instance, a natural number to a float. No. Okay. I mean, just by using rewriting, so to change the type of. Okay. So what does that mean? It means that if an instance of a left-hand side is typeable by some type A, then the corresponding instance of the right-hand side is typeable too, and with the same type. Okay. So if you have these three properties, then you have the same property than the lambda pi calculus that we have seen before. And in the last lecture, we will see some techniques to prove those properties and how they relate to each other. But that's it for theory. Okay, and so for today, we are going to move to more practical things. Okay, so you remember yesterday I showed you this picture with deducti and lambda pi. So deducti is an implementation of the lambda pi calculus modulo rewriting, but it's a minimal one. It's just a type checker. Okay? So it means you have a file. What do you have in a deductive file? It's a signature. Okay, so you declare a number of constants and rewrite rules, and then you may have a bunch of terms, but you want to check the type. Okay. And that's it. Okay. So it's mainly a type checker, and so it's very nice if you want to double check. So proofs that are written in some other systems. And so lambda pi is an extension of deducti with additional features that may be useful to write expressions directly in deducti, or to also help in translating things.
Are you using Bendix completion for this terminating confluent rewrite system?
So we will talk about this the last lecture. Yes, so indeed it may be useful. So I didn't mention this. So I said that we can use rewriting to decide some equation of theory. Okay? But how to find these rewrite rules? Okay? And this was one of the contributions of Knut to provide a procedure that turns equations into rewrite rules in order to find such a rewrite system. And it's not just I decide to orient from left to right or right to left some equation. Okay? It's not sufficient. No? when you do this, you do not get a comprehensive. Then perhaps you need to add more rules in order to get a complete rewrite system. But at the moment, we don't need to enter all these details, but we will come back to this in the last step. Okay, so in this lecture, I'm not going to present you deductive and its syntax. I'm going to speak only about lambda pi. Okay.
Why is this cubic quantity have a dashed line? Is it working for?
Yeah, because this is a still ongoing work. So we don't have an implementation yet. Okay, but perhaps in the coming months, I don't know, Nicolas. Yes, Nicolas is here. He is working on this. So perhaps next year we will have some translation from cubical type acta, cubical acta to T perhaps. Okay. And we are going to see. So we have much more things, but so the base theory is the same in both in deductive and lambda pi. And sometimes we are talking about deductive, but actually it's lambda pi. So, but you can take this as a kind of synonym. Okay, so now I'm going to give you some basic things about how to use lambda pi and which kind of things you can do. Okay. And at the end, I will invite you to open your computer and try to use it. So, so the syntax between deductive and lambda pi is not exactly the same. It's very, very close, but not the same. So the syntax for deductive is very simple. There is no fancy symbol. And in lambda pi, we decided to use Unicode symbols, stations, this kind of thing. So it's more user-friendly. Okay? Also, an important thing is that, so in deductive, you need to provide fully annotated terms. Okay? But it's sometimes it's not very convenient. Okay? And so in lambda pi, we allow to have implicit arguments. Okay, so you can let the system try to guess some of the subterms you actually need to provide. Okay, and so we are going to see all this step by step. Okay, so there is the source code on GitHub. Okay, so you can already check on GitHub this. So to do some exercise, it's good to clone this repo so that you can have all the files on your disk. There is also a user manual you can check, okay, and some open repository for libraries written in lambda. Okay, so installation. So I hope you could install everything already. And you can also compile from the sources. So if you clone and then you just make it. Okay, and so now how to use lambda pi. So there are two ways. I mean, there is a batch mode when call just lambda pi with a check command and then some list of files, and it's going to check the files. But you can also use it interactively using Emacs or VS Code. So for Emacs, so there is a package available on Belpa, so it's easy to install Emacs also. But you can also install from the sources if you want. So I'm going to move. So how it looks like. So it's very, if you know already the system or used it in Emacs, it's very similar. Okay, so here you have your buffer where you edit your lambda.py files. And there is a green zone to show you what has been checked until now. And you can move this green zone step by step and go back if you want. Okay. And here on this window here, you have the current goals. If you are trying to write a proof, then there is the current goals you have to solve in order to continue. And here messages. And you can change the layout if you want. And for VS Code, it's very similar. So you can get it from the VS Code marketplace. And it looks like this. So same thing. So you have your buffer here with green zone for indicating what has been checked, and the goals you want to prove, and messages here. Okay. So now one thing that is important is when you develop some lambda.py files, you may have different several files, not just one. And you need to define in a small file that is called lambda.py.pkg. You need to pick a name for your package. And more importantly, you need to define the root path. So what is the root path? Because all your lambda.py libraries are installed in somewhere on your system. And you need to specify a logical path from the root of this system-wide directory.
Do you still need to do that if you use OPAM to install it?
Yeah, so in case of OPAM, it will be
It will be
set by default. I mean, but the directory where all libraries are installed. But locally in your file, you need this small lambda.py pkg file to define where to install your local files in the system. And so, and as many other languages, so you have you can require some definitions that are in some other files, with the require keyword. But you need to prefix by your root path. Okay, so for instance, if you define your root path as nat.unary, okay, then you need to prefix everything by this root path. Okay. Unless you use the open keyword. Okay, and when you use open, then it will include in your local environment all the iterations of this module here. And then you don't need to prefix anymore. Okay? But in some cases, there may be some ambiguities if the same symbol is defined in two different files. Then you need to prefix it. Okay. So you can find a BNF grammar for lambda.py. Some small remarks. So comments are like in C. Okay. And you can use UTF-16 characters, and also you can have almost arbitrary strings as identifiers if you put them between these curly brackets. Okay. And it's something very useful if you want to translate proofs from one system to the other, because each system has different conventions for defining identifiers, and often some identifier that is valid in one system is not valid in another one. Okay? And this is a way to be able to handle any kind of identifier. And so now what is the syntax for terms? So actually, because we use Unicode symbols, is the same as the syntax, abstract syntax I've shown you yesterday. Okay. So you have this big type. There is no big kind, okay, because the user cannot input terms with big kind. It can be the result of some typing, but not some input. Okay. So for identifier, so as mentioned just before, you can prefix by some module name. Then you have a term application, the abstraction, and the type of an abstraction is optional. Okay, so it means that, and this is one difference with deductive. Okay? If you do not give a type, okay, to the system, we try to declare it. So same thing for product and the other type. Okay? And you have also let's. And you can use a special character, so the underscore. If in some expression you don't want to write everything, you can just put underscore and hope that the system will be able to fill in this hole. So what can you do in NumPy or in DDT? It's the same. So mainly it's about defining signatures. Okay. So it means there are mainly two commands. Very easy. So one to declare or define a symbol, and one to add rules. Okay. So the first one, to declare a symbol. So a symbol, so you have an identifier, some parameters perhaps, and then some type. It can come with a definition or not. Okay. If there is no definition, it means that it is a constant or an axiom. We will see. Until now, I just talk about lambda calculus and dependent types. I didn't explain how we can represent propositions and proofs. We are going to see. And the definition, it can be given by a term, or it can be defined interactively by providing a proof script. And then there are also some information we give to the system about this symbol, like saying that it's a constant. So it means that no rule can define this symbol. But it is opaque. So opaque, what does that mean? But you give a definition, but then you never unfold this definition. Okay? So what is the interest is that usually the proof, when you give a proof of a theorem, the proof is actually a definition, but usually you don't want to unfold the proof. And it's also possible to declare, I'm not going to speak too much about this, but it's also possible to declare some symbol as associative and commutative. It's very useful to represent, for instance, arithmetic, or to encode universes in NumPy. You remember the product rules for universes, where we have type I, type J, then the output type is the max of I and J. Okay? And the max operator is associative, commutative, and has other properties. And then it's very convenient to be able to reason modulo associativity. And associativity and commutativity together, it's a theory that we cannot decide by using rewriting. Okay. So it needs to be managed in some specific way. Yes. And there are some other things that I'm not going to enter the details. Okay, so let's see some examples. Yes.
Is there no hope of generating a rewriting system to reorder the factorize associative operator according to some procedure.
So if you have associativity you are going to see alone, you can handle this as a rewriting. But if you have associativity together with commutativity, then you will get a loop. It does not happen. There is no rewrite system that terminates for associativity and commutativity. So let's see some very simple examples. No, if you want to represent the type n of natural numbers, like P and O, so you have a constructor 0. So you declare the type n. So you declare a symbol n of type big type. Okay. And then the constructor 0 and successor, and you give the types. Then addition, for instance, so say, okay, I have a symbol plus with this type, and you can use some notations, fixed notation if you want. So these are just a declaration. Okay. Later, you can add rewrite rules to define addition or multiplication. So which kind? And this is exactly what I wanted to say. So the second command you have is to add rewrite rules. Okay. And the rewrite rules, so it's just okay. So you have a left-hand side and a right-hand side. Okay. And so, for instance, you can define the plus symbol that you have declared before by adding rules. Okay. You say x plus 0 reduces to x, and x plus 6 of y reduces to x plus y. Okay.
How do you input the symbols like hook arrow in the editor?
This one?
Yeah.
So we are shortcuts in Emacs or in VS Code. In Emacs, it's just a dash greeter.
Okay.
Yeah. So in the documentation, you can find the list of shortcuts to define this.
Okay.
And so I mentioned earlier that a very important property we have to make sure when we use LambdaPy is that the combination of beta reduction and the user-defined rewrite rules is a confluent system. Okay? It means that every term has at most one normal form. Okay? And so it's a difficult problem. Actually, it's undecidable. Okay, but we can try to check that to some extent we have this property. And so in LambdaPy, there is some algorithm that is going to try to check not full confluence, but local confluence. Okay. So local confluence means so let me. So confluence, you remember, perhaps. So you start from a term T, you reduce to possibly two different terms, and then you need to be able to close this diagram. So this is confluence. Okay. Or it's equivalent to the church procedure. Yeah. So I write C for this one. And local confluence is when you just consider one step. Okay. This is local. Okay. So of course, if you are confluent, you are locally confluent. But the converse does not hold in general, unless you are terminating. So if you have a terminating relation, confluence is equivalent to local confluence. Okay. And so we try to check that the rules that are given by the user preserve typing and also are locally. It may fail. Okay. Because these problems are not decidable, so we try our best, but we fail in some cases. Okay. So this is here, I mean, the standard definition that you would write, for instance, in ROC or ACDA or LIN, okay? It corresponds to a definition by induction on the second argument. Okay? So in ROC or LIN, it's using some matching constructors. Here, it's each case is reclassified. Okay? But we can do much more in LambdaPy because, for instance, we can also have the symmetric rules, okay, which is not possible in POC. So when you do this, you see that there may be different ways to rewrite a term, while in the case of POC or LIN, no, it's completely deterministic. Okay? And so to prove confluence is more complicated in this case, but that's possible. And also it's possible to do matching on defined symbols. So for instance, associativity, okay? You can have a rule for associativity like this one. And finally, you can also have matching on non-linear patterns, okay, which is not possible in ROC or LIN. So that's nice, but at the same time, and we will see more, to have non-left linear rule is problematic in order to prove confluence. And we will see, by the way, that actually, as soon as you have a non-left linear rule, you are losing confluence on untyped terms. Okay, so I was mentioning that we try to check local confluence, no, except if you have higher order patterns and commutative associative symbol. It's not implemented. And so, what is higher order pattern matching? So we can also do this, no? So here is a simple example. If you define some derivative operator on real functions. Okay. And then with these rules, we can find what is the derivative of the composition of sinus with some function f, okay, or what is the derivative of some constant function. Okay. And this is what we call higher order matching, okay, because you are matching on lambda abstractions. Okay. And also you are checking whether some bound variables is occurring or not in your instance, in your pattern. So here we are checking that, well, actually there is nothing to check, no, because there is only one bound variable, so we can take any term here for f of x. But here we are saying, okay, we want to match some variable v, but does not, because it's empty here, does not depend on x. Okay? And like this, we can capture a constant function. So this is the kind of rewrite rules that you can have and use in LambdaPy. And so to go back to the question of deciding some equational theory, so nice example, well-known example, is the group theory, pre-group theory. Okay. And so where you have so a group with a neutral element, composition, and inverse, and with all these rules, okay, you can decide the word problem on group theory. Okay. And so it's possible to write this in LambdaPy. But you can see that this system is non-left linear. Okay, and so what else can you do in NumPy? You can make queries and check some assertions. Okay. So you can, for instance, if you write print some identifier, then you can get some information about some symbol, what is its types, its defining rules, and so on. You can ask the type of a term, and you can also ask the system to compute the normal form of some term. And finally, you can check things. So either you can check some typing judgment or some equivalence between two expressions. So it may be useful to test if you have written a number of rules and types and so on to make sure that you didn't write something wrong. Okay. Okay, so now I would like to come to the problem of checking proofs. Okay, until now, we didn't speak about proof. And so, now we have defined this framework, the LambdaPy calculus rewriting. Okay? We want to use this, and we will going to see tomorrow how to use this to represent propositions and proofs from different systems. And so you have seen a little bit with Florian, the previous lectures. So the first thing to do is to introduce a type in LambdaPy to represent the propositions of your system. Okay? And so it means so you start by saying, okay, I have a symbol of that is a type. Okay. And you may have constructors on proposition to build proposition like conjunction functions. Okay, so you say, okay, I have conjunction symbol. It takes two propositions as arguments. And return a proposition. Okay, so like this, you can build propositions, conjunctions, and some other things. Okay, but now, so you would like to represent a proof of some proposition. And the way we do this in NumPy is to use the so-called Curie-Award or Curie-Lebrun-Award isomorphism. So we are going to identify propositions, types, okay, and then a proof. We are going to represent proofs as terms, lambda terms, and so proof checking is going to be reduced to type checking. Okay, but how to do this? Because prop. Okay. So if I take, for instance, I don't know, if I have a proposition x and y, where x and y are propositions. So this is of type prop. Okay. You remember the hierarchy that we have. So this is an object. Okay. So this is the family, a type. Okay. But objects are not types. Okay. So if I want to provide a proof of a conjunction, okay, I need to interpret this as a type. Okay. And this is what we are going to do. Okay. I introduce a new symbol. Okay. to interpret propositions into types in the logical framework. So here with POP, we have a deep embedding of propositions, the logic, but now we need also to interpret this deep embedding of propositions as type in the logical framework. Okay. And then, so we can, once we have done this, and we are going to see that we can actually define this function proof. Okay. But we will see this tomorrow, mainly. Meanwhile, so we can already add axioms to represent possible axioms in our logic. Okay? So, for instance, we can say that I have an axiom ref saying that two elements are equal. I mean, one element is equal to itself. Okay? I can have an axiom for monotony, okay, for the monotony of the successor function. Or I can also have at the meta level in the logical framework some induction principle on that one. Okay, so it's just a declaration. I add this, it's like a new axiom that I add system and that I can use to build proofs. And so I mentioned a little bit this before. So what is the difference between stating an axiom and proving a theorem? So in this case, the only difference is whether you give a definition or not. So for instance, if we keep the example of natural numbers, we may want to prove that 0 plus x is equal to x using the definition we have seen before of addition on natural numbers. Okay. And so this is a proposition, so an object of type pop, okay, and we want to using the proof symbol, so this is a type. Okay. So it makes sense to try to find an expression having this type, okay, because now we have a type by applying this proof. And so proving this is just giving a definition, so it means providing a lambda term that has this type. Okay. And for doing this, you can use the axioms that I mentioned before, like induction, reflexivity, and so on. Okay. And to help doing this and not writing lambda terms only, okay, we provide a tactic language. Okay. So when you declare a symbol or you try to find something, then the system may generate a number of problems that you have to solve in order to make sure that your declaration or your definition is correct. Okay, it means typable. Okay. So you have two kinds of problems. You have typing goals. The typing goal, it means that as you have perhaps some assumptions, and you are looking for some expression of type B. Okay. This is the case if you want to prove a theorem, and then your theorem is a proof of some proposition, so it's B, okay. And you are looking for a term having this type. Okay. So when you start a proof in lambda pi, and it's the same in rock or lin, actually, you have to solve a problem like this. Okay. But you may also have unification goals. It means that for something to be typable, two expressions need to be equal. Okay. And the system did not succeed in proving those equalities. In this case, you have to possibly help the system to do this. And to do this, so these problems, you have a number of tactics that you can organize in a like way to solve this problem. So then you can write in lambda pi things like this. For instance, to prove that 0 plus x is equal to 0, with a definition by rewriting addition. Then you can say, okay, you apply induction, and then in the first case, so when x is equal to 0, I just apply reflexivity. So 0 plus 0 is going to compute to 0, okay, and is syntactically equal to 0. And in the induction case, then you have a little bit more work. So you assume, so you have to prove that if it's true for x, it's true for x plus 1. And so you assume the induction hypothesis, but you apply, and then you finished. So it looks like this.
Sorry, back one slide.
Yeah.
So I'm a bit confused by the unification rules.
Yeah.
What you need to prove here is a definitional equality.
Yes.
But how can you prove a definitional equality?
Yeah, so at the moment, I mean, you have this internally.
I mean, what does it give you to prove? Does it ask you to prove it as a proposition?
Yeah, so if you get a goal like this, it means that perhaps there are some missing rules, and the system was not able to identify two terms that should be. So actually, at the moment, there is only one tactic to solve this kind of goal, and it's applied automatically. Okay.
So to be clear, the user doesn't prove this as a proposition or equality, and then it's reflected. Because this
well,
would be
you could
consistent
imagine
with cubical criteria and so on.
Yeah, you could imagine to do this kind of things, but it's a framework, so it's kind of agnostic about what can be. So okay, and so what are the currently existing tactics? So you can simplify an expression, so applying beta addition of the user-defined rule. And well, a general refined tactic, so you say, well, my proof is by applying this theorem and so on. So you have a number of tactics that are similar to what you can find in Lean or Pop. But you have a much smaller number of tactics. And also you can do some rewriting. So here rewriting is if you define a propositional equality. It's not about the definitional equality, which is implicit. Okay. But if you have some explicit equality, I mean logical equality, you want to formalize, then as soon as you provide a number of information, then it's possible to apply a rewrite tactic, like you can do, for instance, in SSReflect in ROP. And it's also possible to call external provers, automated theorem. Okay. But at the moment, if you do this, it's just going to generate new axioms. So you trust the automated theorem prover, so it's not so nice. Because at the moment, so Y3 is not providing any certificate, but ultimately what we want to do is to get certificates from automated theorem provers and don't generate axiom. But it may be okay, so now let's see some interesting examples of things you can do with NumPy. So for instance, you can define inductive recursive types. Okay, so what is it? It's an inductive type that you define, but at the same time, that depends on some function that you define on the type that you are defining. So very well-known example is, for instance, if you want to define the type of lists without duplicated elements. Okay. So for lists, you have two constructors, nil and cons, as usual, but now in the cons case, you want to make sure that the element X that you add in the list does not belong to the tail of the list. So it means that you need to define a predicate does not belong on induction to the type that you are currently defining. Okay. So this is what we call an inductive recursive type. Okay. But it's very easy to do this in LambdaPy because symbol declarations and rules are completely separated. Okay. So it means that you can make a declaration and then later some rules and even later some other rules on the same symbols, okay, as long as everything is preserving all the properties. So it means that we can start by defining the type L that we want to define, and then the predicate on L, okay, the constructors, and then only later we can give the rules that are defining this predicate. And by the way, okay, there is also a command inductive. So before I mentioned, okay, the natural numbers, we can represent this as declaring a type and then declaration for each constructor. But actually, we want more. We want also induction principles and rules for induction principles for cut elimination. And this can be done by just one command. So if you give a declaration like this, you say inductive n and then the constructors, and the system is going to generate all these things. It's equivalent. So a declaration for each so type and constructor, the induction principles, and then the rules defining the induction.
Because your limiter goes to prop, or you cannot limit this type.
Yes. The question
is this intentional, and where does the prop come from? Because I thought it was user defined. So
it's user defined.
So at the same time, it's automatically used by the system. So
yeah. So it's automatic if you have. So there are some other commands I did not mention, but you need to tell the system that you are using some symbol prop, and then it can generate some induction principle in this type. Okay. So this is a facility that is provided. Okay. And at the moment, so it's limited, but you still can do quite something. And of course, I mean, because you have to define everything, it's a logical framework. So at the beginning, when you start LambdaPy, it doesn't know nothing about prop because it's user defined. Okay. And not even types. So what are the types if you want to encode rock or link proofs in LambdaPy? So you need to introduce some more things. And you can also, if you know this, perhaps encode inductive types. So well-known example is how to represent typed context. Okay. So here in this case, it's called inductive because I mean you want to define a type of context. Okay. And how is built a context? So you have the empty context, and then you can extend. So if you have a context gamma, is like a list of types. Okay. And you extend it with a type, but the type depends on the context. Okay. So you have some context gamma. If you have a type in the context gamma, then you get a new valid context. Okay. And how to define types? So now types they take as argument the context. Okay? So you have a constant, which is the universe, okay? For your type system. It's a simple example here. And then you have a product. Okay? How to build a product. So you have a context. You take a type in this context. So you see here, I do not write all the types. You know, there are many things that are implicit here. Okay. So, but if you check the type of composition, you will see that A is of type of gamma. Okay. And then I take a type in the context extended with A. So this is the codomain. Okay. So what we are formalizing here is just PXA P. Okay. So A is in gamma. It's a type in gamma. But B, okay, is extended with A. Okay, so B is typeable in gamma with extended with X of type A. So the interest of this kind of definition is that to formalize only well-typed types, okay, and context. And probably, I mean, you mentioned this kind of things in your talk. Okay, and so it's possible to do this so in lambda time. Okay, and so to summarize, here I mentioned so all the features that we have in addition to here deductive, okay, so a more friendly syntax, but still we can read on out deductive, okay, so it's compatible. So we have implicit arguments. I didn't mention this, but also we can apply type coercions in case of type mismatch. It may be useful. For instance, if you want to translate a system that is using some implicit subtyping into deductive, so you need to rebuild the subtyping information and make it explicit. And this is the way to do this. Okay, so when you have proof tactics, induction, some local confiance checker, and some other things. Okay. And so I think I'm going to stop here.
So that's a relationship.
No. So there exists some termination checker, but it's not part of lambda pi. But it's limited because it's very difficult to prove automatically termination of arbitrary
Obviously, evoke as existence is right.
Yeah, no, exactly.
Supervise so.
Yeah.
So in Acta, you have this without a flag to restrict unification, because without it, you're able to define, to prove uniqueness of identity proofs. Is there something similar here?
So can you repeat this?
Yeah, so whether you can prove uniqueness of identity proofs in Acta depends on your unification algorithm.
Yeah.
So you have this without K option to restrict your unification algorithm so that you cannot prove this. Is there something similar here, or do you not run into this?
So I mean, in lambda pi, I mean, the unification is much simpler. I mean, we don't have all the things that are in Acta.
The pattern match.
Yeah. So yes, this is kind of first order unification or restricted fragment of higher order matching. In general, it's not decidable, but if you restrict to Miller patterns, you get something decidable. And this is the kind of things we implement in lambda pi. But so the relation with K, I mean, it's it's just lambda pi calculus. Okay, so you don't even have at the beginning a notion of K because you need a propositional equality of this kind of thing.
But for example, if you define an identity type as one of these inductive types, would you be able to prove axiom K?
No, I don't think you can derive axiom K.
So you generate the eliminator, and what is the eliminator which is generated for the identity type? Is it J? Is it the
question.
Pauling mooring or the?
This is a good question. But we need to understand because, I mean, so currently induction principle is generated in the prop type that is defined by the user. No? And so is it what you, well, I don't know how to answer this question. So we have to try and see what's happening. Okay, but the thing is that you need to define, I mean, your prop universe already.
How do you ensure that you don't get a contradiction from the user writing rules?
We do not check this. I mean, this is the responsibility of the user. I mean, like in any other proof assistant, no? You may introduce also in Rock, Agda, in some assumptions that are wrong. Okay. So here in this context, you have perhaps a higher risk to get problems because perhaps your system is not confluent or does not terminate or these kind of things. Okay. And perhaps in systems like Rock and Lean, so you have more guarantees for this. They also have algorithms to check, for instance, termination, which is not the case here. Or the fact that definitions of functions are restricted to matching on constructors. This implies a number of properties like recurrence and also to some extent consistency. But yes, there is no guarantee.
So usually, if I write a program in LambdaPy, is there a handful of extra meta theorems to ensure confluence and such that I should always?
Yeah, so you have a lot of literature about this.
Okay.
And we will see on Thursday how to prove this property.
Yeah, related to the consistency issue, how difficult is it to have a model generator for LambdaPy? I mean, thinking of Isabel, for instance, Isabel is very easy to evoke nitpick or to generate model, so you know that the actions are consistent.
A model of LambdaPy?
Yeah, how would the model generation for LambdaPy look like? Or do you have plans to have a model generator integrated? Or
yeah, so I'm not expert on this kind of question. So I mean, probably Ambros is a better person to answer this kind of problem. I don't know if, to some extent, there are general models for something that looks like this. You know, so it's LambdaPy calculus, modulo equations, but I'm not sure there already exists a general theory for any possible equations.
I have a question for people who are asking these things about consistency because I'm confused. So do you expect the tool to tell you that ZFC is consistent if I type in the axioms of ZFC? I mean, what is the why do you expect the tool to even do anything about consistency?
I expect to have some guarantees of my translation.
Of the translation?
Yes. Between, I don't know, Agda to Lean or something like this.
How does that relate to consistency?
Because it passes through the dot key and for LambdaPy, and if this step is conservative, then it should be consistent.
But actually, in this case, you don't need, you don't really need to let's say you translate something from, I don't know, from Rock to Agda. Okay. if in the end Agda is checking what you are providing, then you don't care how you got it. No, you just need to make sure that what is given to Agda is really what you wanted. Okay. But in the end, I mean, Agda is going to check it. Okay. So assuming that Agda is bug free, okay, then you can be confident. Okay.
So until Agda checks it, I have no idea if my translation worked.
Yeah, but so we try to check things also in inductive. But that's better for both, of course, but it's actually not necessary.
Just a curiosity. I can specify these rules, and the system tries to check their confluence. What happens if the system fails? I can still use the rules. I can maybe.
Yes, it's just a warning. It's just a warning. It's going to say that here it's going to give you an example of a term that reduces to two different normal forms. Okay. And then you should do something of that bit. So you can continue, but your system is completely broken. Because if you lose confluence, you lose many properties.
I was wondering, a case in which there is confluence, but it's not trivial to prove, so maybe the system failed.
But then usually, I mean, local confluence is going to fail, and unless you have to do very big computations in order to find an example, but most of the time, I mean, it's going to provide find quickly a counterexample. I mean, then you can see, okay, I forgot to add this or that rule to your system to get something complete.
It doesn't actually break completely. It only breaks half of the things, right? It breaks completeness, but it's still sound.
But you lose also subject reduction for beta.
Oh, I see.
Yeah. So no, you are not in a good state if you lose confluence. No more questions? Okay, so thank you.